Hello everyone, in this video we'll find the state equation based on the coefficients beta and kappa. Let's get started. In this problem, we have information about beta and kappa. Beta is equal to this expression and kappa is equal to this other expression. In order to find the state equation, first of all, we must remember what the definition of beta is and for kappa. For example, beta it's equal to 1 over v times the partial derivative of v with respect to p at constant pressure. This is the expansion coefficient. If we solve this term for the partial derivative of v, it will be gotten this other expression. The partial derivative of v with respect to t at constant pressure it's equal to beta times v. Same thing for kappa. If we remember, kappa is equal to minus 1 over v times the partial derivative of v with respect to p at constant temperature. If we solve this equation for the partial derivative of v, it will be gotten this expression. Now, we must remember, as we saw in previous video, if we suppose, for example, that v is a function of t and p, we can calculate its total differential like that. The total differential of the volume will be equal to the partial derivative of v with respect to t dt plus the partial derivative of v with respect to p dp. So now we have already expressions to replace this partial derivative. We have it in here. The partial derivative of v with respect to t it's equal to beta v, and the other partial derivative it's equal to minus kappa v. If those expressions are in place in this total differential, it will be gotten this term. In this part we can factorize the variable v. If we do that, we'll get that dv is equal to v times beta times dt minus kappa times dp. So this v that is multiplying in the right side can pass to the other side, dividing like that. So now we can rewrite this equation with the information that we had in the problem. Beta is equal to this expression and kappa is equal to this other expression. If those expressions are in place in this equation, it will be gotten next. Now, what is the objective in this problem? In this problem, we need to find the state equation. In order to do that, it's important to integrate this differential equation. However, it is impossible to integrate exactly like we have like that. Because, for example, this left side, it's possible to integrate easily because we have the differential of volume over the volume. If we try to integrate this term, we'll get natural logarithm of the volume. But we can't integrate in the second term. Why? Because our function is of two variables. If that happens, it is impossible to integrate directly. We need that our function depends only of one variable. In this case, we can't suppose that v is constant because previously we've said that V is a function of temperature and pressure. So that tells us that V isn't constant. It depends of the temperature, but we don't have any expression to replace it and then integrate it. Same case we have in this other expression. We don't have a term to replace it, the volume in here, and that only depends of the pressure. Remember, actually V depends either the temperature and the pressure. But we can arrange this expression in order to find another equation that becomes easier to integrate. In order to do that, let's go to solve all those problems. After that, we need to rearrange the terms, like we'll show that in a moment. First, let's go to multiplying this term to its terms in the brackets. If we do that, we'll obtain this expression. Just we're making the multiplication in its case. Then, in order to not to work with fractions, let's go to multiplying all those fractions by the minimum common multiple. In this case, the minimum common multiple will be this term, V times P times T cubed. If we multiply all the equation by this term, we'll get that the differential equation that we must to solve is this that we have in here. Now let's go to arrange some similar terms. For example, in this case we have P times T cubed. We have another term which has T cubed, so we'll pass this term to the other side with positive sign. And the left side will get like this. Now let's go to factorize T cubed. If we do that, we'll obtain this expression in here. Now, if we remember, this expression in brackets, it's pretty similar to the product rule. If we remember a product rule, we can rewrite this expression like this. This expression can be written like the differential of P times V. If we solve this term, we'll get this expression that we have above. And the left side stay the same. Now, in the left side, we can observe that we have either T, P, and V. We have the three variables that it involves in the equation. If we notice, this other term also have all the terms. So let's go to aggregate it with the term that we have in the left side. So this that is adding in the right side plus negative in the other side. Exactly like this. In order to notice better what's happening with variables and the differentials, let's go to do a change variable. For example, let's commit that W is equal to P and V in order to rewrite the differential equation like this. in here, the w, it's this term that we have in here. Instead to write a pdv, it's w. In here we have also pdv. Also, this term becomes w. And the next step that we've wrote, it's divided all the equation by t squared. That is shown in here. So for that reason, we have this expression. So remember, w is equal to pv, and in here we have pv. And then this differential equation was divided by t squared. Why by t squared? Let's go see it in a moment. If we solve this division in the left side, we'll get that t cubed over t squared, it's t, minus w is the same, and t squared over t squared it's equal to 1. So for that reason, in this term we have only w. And that is equal to, in its case, each term is divided by t squared. So in here we have t over t squared, it's t but in the denominator. So now, this part over here make us think that the quotient rule for differentiation. If we remember the quotient rule, we know that the differential of u over v is equal to v times du minus u times dv over v squared. This is the rule for a quotient. If we realize in our expression, we have in here a similar term that we have in here. The difference is that we don't have any quotient in here. In here we have v squared, but in here we don't. In order to solve that problem, we can divide again by t over t squared, but in all the equation. If we do that, if we solve this multiplication, it will be gotten this expression in here. So now this term is very similar to this rule. So we're able to rewrite the expression like this. We have now the differential of a quotient, and the right side it's the same. So now, in order to solve the right side, we must remember an important equation, an important theorem in differential equation. If we have a differential equation like this, if this is an exact differential equation, it must achieve this condition: the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. In addition, we can see this equation like the partial derivative of f, that is the function which we're calculating the differential with respect to x, dx plus the partial derivative of f with respect to y, it's equal to 0. In this case, this part is the role of n, and this part is the role of n. In here I forgot to write dy, but that is the main idea. With this fact, we can calculate what is the partial derivative of this term with respect to p, and that expression must be equal to the partial derivative of the other expression but with respect to t. If we do that, we'll get the next expressions. The partial derivative of the first term with respect to p will be equal to 3a over t to the 4. In this case, 3a and t are constant and we need to derive only p with respect to p, but that expression is equal to 1. For that, we'll get only this expression. Then, let's go to calculate the other partial derivative. We must calculate the partial derivative of this other expression. Minus a is a constant, so we need to calculate just 1 over t cubed. But that expression could be written like t to the minus 3. If we derive that expression, minus 3 comes in here multiplying and the power decrease just in 1 unit. So in here we had minus 3 minus 1, it's minus 4. Minus and minus is positive, so we have 3a times t to the minus 4, but that could be translated in the denominator with positive power. Now we have in here our original differential equation. We've proved that this part is exact, so we can solve this differential equation. In order to do that, we know that we have a function. We don't know what that function is, but we know that its partial derivative with respect to t is equal to this part in here. So let's go to do that. The partial derivative of a function as we are looking for with respect to t is equal to 3ab over t to the 4. Now let's go to integrate this part with respect to t. We have that expression. The integrate of this part must be equal to the integrate of this other part. In here we can cancel dt and dt, and the differential could be cancelled too. And in the right side, we must solve this integration. In this case, 3a is constant, and p could be considered a constant because we integrate only with respect to t. So, integrating that part, we'll get that f, our function that we are looking for, f is equal to minus a times p over t cubed plus gp. In order to find what is this expression g of p, we need to calculate the derivative of this expression, but now with respect to p. If we do that, the partial derivative of f with respect to p is equal to a and t are constant, so the derivative of p with respect to p is equal to 1. So for that we have only this term. And the partial derivative of g of p with respect to p is equal to g prime p. So now we know that this part must be equal to the coefficient that we have in the p. Let's go to do that. So this part must be equal to minus a over t cubed. This term and this term could be cancelled because they are the same and they are in opposite side of the equation. So we have that g prime of p is equal to 0. Integrating this expression, we finally find that g of t is equal to an arbitrary constant. So that means that the function that we are looking for is equal to f it's equal to minus ap over tq plus c. So that is the function that we were looking for. If we replace it in the original equation, this part we know in previous operations, and that is the right side of that equation. If we calculate this differential, we must obtain the expression that we had before of all this process. In this part, we're perfectly able to calculate the integral because we have only differentials. We don't have anything multiplying the differentials or something like that. So in this part, it's perfectly integrable. In the left side, we have the integral of d w over t. So the differential can cancel with the integral, and we only have w over t. And that is equal to the integral of this part. The integral could be cancelled with the differential, and we have exactly the same expression that we have into the differential. In here, we just change the order of this sum. Now, we must remember that w is equal to pb. If we replace this expression again in here, we'll get that pb over t is equal to the expression that we have in the right. If we translate this p that is dividing this side, multiplying to the other side, we'll get this other expression. And this expression that it's subtracting in this side pass positive to the other side. And we have a common factor, in this case is p. If we factorize that term, we finally get this expression. And this is finally the state equation that we were looking for, based with the expansion coefficient and the compressibility coefficient beta and kappa. So that's it for today's video. Thank you very much for watching, and see you next time. Take care.